Alright, 11.1 is tangents. We're going to talk about different lines or segments inside a circle. We're going to talk about specifically tangents, secants, and chords. And to do that, we're going to start off by remembering or redefining what a circle is. It's a set of all points in a plane that are equidistant from a given point. That's called the center of the circle. And you write it, you can write it out using circle C, or you can draw a circle with a dot in the middle of it and then the letter of that center point on it. All right, and then so now let's look at chord, secant, and tangent, and also this point of tangency. And a chord is a segment whose endpoints lie on a circle. So if I pick any 2 points on the circle and I connect them, that would be a chord. Okay. Some things to know about this is that a diameter is also a chord. It's a special kind of chord. Right. So diameter is a special type of chord. A secant is a line that intersects a circle at 2 points. So that would be something where it actually crosses and goes past 2 points. All right. Now the next one is called a tangent line. Now it's a line that comes down and just touches the circle only at 1 point. So that would be a tangent line. Okay, that would be what we call a tangent. Now this point right here, that's the point of tangency. That just means that's the point where the tangent line and the circle meet. Okay, so that would be my point of tangency. All right, so let's just kind of look at these and redo some definitions, some naming stuff. Name the following tangent. That's going to be line xt. Remember we show the arrows on both ends. Point of tangency is going to be t. A point in the interior, that's going to be this point I right here. And then a point on the exterior of the circle would be x. Alright, now we're going to look at this theorem, and it says if a line is tangent to a circle, then it is perpendicular to the radius drawn to the point of tangency. So let's look at a picture of what this means. So if I know this is the segment is tangent to the circle, that means this angle right here is 90 degrees. Okay, so what we would have to do is we'd have to use Pythagorean Theorem to find x, because I do have a right triangle. The only kind of difference on this is that there's a 5 right here, because that's a radius. This radius is the same as this radius. Okay, so to do this, I know that 5 squared plus 12 squared is equal to AC squared, that whole length. I'm going to kind of ignore this, and I'm going to come back to this 5 and the x for just a minute once we get this. So if it makes it easier for you, instead of calling this 5 plus x, we can just say that this is some number. I don't know, we can throw that as count that as a y. So I would say 5 squared plus, I'm going to go ahead and do it this way, 25 plus 144 would be equal to y squared, which would be, this comes out to 169. So the square root of y, or square root of 169, would be 13. But remember, y is the whole thing, so it's x plus 5. So then I would take 13 is equal to x plus 5. Subtract the 5 from both sides, we get that x is actually 8. Okay. Next theorem that we're going to go ahead and look at, and I'll show you the picture. If 2 segments from the same exterior point, so here's my exterior point P, right, and notice that you got 2 segments that are coming out from that point P. I got PQ and PR. So if they're coming out from the same exterior point, then these segments are actually congruent. So to solve for x, you would do 2x minus 3 is equal to 27. You add 3 to both sides, you get 30. Divide by 2, you get x is 15. Okay, so just some theorems that we're going to use and that you'll need to be familiar with. The next thing is when circles are inscribed in polygons, the polygons are said to be circumscribed. In such polygons, each side is tangent to the circle. Let me show you what I mean. Alright, so here is my triangle, and I have a circle that is drawn inside. That's what we call the circumscribed. Okay, and so all of these points are my points of tangency for each of these. So K is the point of tangency for TW, L is the point of tangency for TR, and M is the point of tangency for WR. Alright, so now we're going to use this. If the perimeter of triangle TR is 5, I know that TK is 3, and WM is 9.5. I have to find the rest of these. So, with that theorem that we just looked at before, says that if this is 3, this has to be 3. This is 9.5, this is 9.5. Now, I don't have anything for RM or MR and RL, but I do know that these two segments would have to be congruent. So we can set this up and let those be x's. So kind of figuring all of this out, I know that I have x plus, if I go all the way around to find the perimeter, x plus 3 plus 3 plus 9.5 plus 9.5, all of that has to come out to be 50. So kind of combining this, adding all of this up, I get 2x plus 28 equals 50. If I subtract the 28, I get 22, so that tells me that x is 11. So then I know both of these segments are 11. Now it asks us for TR, so I would have to do TR is going to be equal to 3 plus 11, which would be 14. Alright, number 5, got several things that you will need to be able to find using those theorems we just went over. OA, you know, this is from O to A is 12. OB is 6. And you know that the measure of angle BAC, this whole angle right here, is 60 degrees. Okay, so if OB, just as an example to kind of get you started, I know OB is 6, that means, and that's a radius, so that means all of these radii, OC, OE, OD, those are all going to be 6. Okay, so you would kind of use that, use the fact that you have a 60 right here to 60 degree angle to find all of these. You can check with me in class to make sure you did it right.